In Verilog, switch level modeling is one of the style of writing the program where the logic is first of all converted into the is converted or represented in with the help of transistors. So, for example, this particular thing it shows a NOT gate or nothing but a simple inverter where the input is in and output is OUT. Output is complement form of the input, which is being represented nothing but the NOT gate, which is represented with the help of transistors. So lower is the NMOS transistor and upper is the PMOS transistor. So in switch level, whatever may be the logic that we are going to see, any digital logic is represented in the form of transistors. That too the MOSFETs. So here, when writing the program in the switch level, we are going to instantiate the transistors here, the NMOS with the help of small letters, as the Verilog is case sensitive. These are the ideal representations for the MOS switches, ideal MOS switches, NMOS, PMOS, CMOS. CMOS transmission gates we are going to use. So that's why CMOS. If at all we are going to use the resistive MOS switches, we can instantiate those resistive MOS switches by RNMOS, RPMOS, or CMOS. We can also use the bidirectional switches where the transmission is going to be taken place on either side. So these bidirectional switches are TRAN, TRAN if 0, and TRAN if 1. And resistive bidirectional switches can also be used. We can instantiate those resistive bidirectional switches as or TRAN if 0 or TRAN if 1. So when we are going to see the circuitry at the transistor level, we are going to use power supplies, VCC and ground. So we can't use VCC and ground directly. Instead of that, we have to use the keywords supply 1, nothing but VCC, and supply 0, nothing but the ground. And when we are going to see the circuitry, some of the transistors form the pull-up section and some of the transistors form the pull-down section. So directly, we can use the keyword pull-up and pull-down for those transistors. So these are the certain switch level primitives that we are going to use in Verilog. The ideal MOS switches, resistive MOS switches, ideal bidirectional switches, resistive bidirectional switches. Here, it shows the symbolic representation of NMOS switch and PMOS switch. In maybe IN in stands for the input and OUT out stands for the output. So source, if we are going to take in as a source and out as drain, this control nothing but the gate. So when we are going to see the operation of NMOS conducts when its gate to source voltage is positive. Means the NMOS goes into on state when its gate to source voltage is positive or nothing but logic 1. Similarly, PMOS conducts when its gates to source voltage is negative. So here the gate is nothing but control signal. This is the symbolic representation of PMOS showing the bubble at the gate. So this PMOS conducts when its gate to source voltage is negative or nothing but logic 0. In this way, we are going to use the transistor symbols when we are going to represent the logic with the help of transistors, MOS transistors. So as already said, that we can use the pull up and pull down we can instantiate the, we can use the names. Here X stands for the net, okay, which is connected to supply 1 through the resistance. So we can simply write it as pull up of X. Similarly, if the net X is connected to supply 0 through a resistance, then we can use the pull down of X. Like that, we can represent in the program. Coming to, this is the simple circuitry that shows an inverter, nothing but the NOT gate using CMOS logic. So here we are going to have a pull down network, nothing but the NMOS transistor, and pull up transistor, nothing but the PMOS. So when input equals to logic 0, let us see its operation. When input equals to logic 0, so NMOS conducts when gate to source voltage is positive and PMOS conducts when gate to source voltage is negative. Here positive nothing but we can treat it as logic 1 and negative we can treat it as logic 0. So when input equals to logic 0, then upper transistor goes into on state and the lower transistor goes into off state. So thereby the supply 1 is directly connected to the output via the transistor QP upper transistor, the 2 PMOS transistor. The current flows from supply 1 through the on transistor and to the output. So this current we can call it as the source current as it is connected to the source. As upper transistor is in on state and it is responsible for making the output to go to logic 1 state, we can call this transistor as the pull-up transistor. Means this particular transistor, when it is in on state, it is responsible for making the output to go to logic 1. That's why the name we can call it as pull-up. Similarly, when the input equals to logic 1, so the upper transistor goes into off state and lower transistor goes into on state. And when we are going to see the upper transistor is in off state means we can treat it as the open circuit and the lower transistor is in on state, we can treat it as the closed circuit. So supply 1 is totally disconnected from the output because the upper transistor is in off state. Coming to the lower transistor, it is in, as it is in on state, whatever may be the output voltage at the out terminal, that will be pulled down to logic 0, nothing but supply 0, through the transistor QN, nothing but NMOS transistor. So also we can say it as when Q1 is in on, this particular transistor is responsible for making the output to go to logic 0. So that's why the lower transistor, we can call it as the pull down transistor and the upper transistor, we can call it as the pull up transistor. So writing the program for the CMOS inverter at switch level. So module name is INV. We can use any other name. Input IN in followed by the output OUT. So output and inputs are scalars here. So output out OUT and input is IN in. So A and B are the nets here. A is a net that is connected to supply 0 and B is another net that is connected to supply 1. So A is a net connected to supply 0 and B is another net connected to supply 1. Here we are going to use two transistors called as NMOS and PMOS. We are instantiating the ideal NMOS switch or transistor which is used as a switch, a transistor which is used as a switch. Then within the parenthesis, we have to represent the output A, the actual input E, and then followed by the control input. Control input is the input that is given to the gates. We can call it as the control input. IN in is the control input, and the actual input is B for PMOS. And IN in is the control input, and A is the actual input for the NMOS. So, NMOS within the parenthesis output, actual input A, and the control input IN in. PMOS output is out, actual input is B, and the control input is IN in. And we are going to end this particular module.